Okay, today is October 6, 2025. That's 9:42, Physics 6. And let's start sharing the screen here. Here is the syllabus. That's the 10th meeting in the semester. Okay, and the 6th week as well. Let me both face this line. And we're going to start chapter 4 now, which is laws of motion. Laws of motion. That's when we start to talk about force, the concept of force, okay? Chapter 4, and let's go. The notes. Yeah, let's not forget that the exam is the day after tomorrow. I'm gonna take away, remember, we're not gonna have lab 1 in this first exam. We're gonna leave lab 1 for the next exam, for the second exam. And let's see, I'm gonna put a question mark here because I do not know how many labs we're gonna cover until exam second, right? So I'll give you a break and a little bit less of material. And let me know if you're prepared for the exam. Okay, we still can postpone it, but for one more week, but I would rather we don't do it. So let me know how you're feeling about this exam, okay? It's just chapters 1 and 2 of the book. And here you go. So we're going to start chapter 4 today. Chapter 4 today, laws of motion. And let's go back to that table that I dropped in at the very beginning of the course. Okay, let me write that down here. Lab 1 report is due, let's see, wait, no, they don't do this, on October 15th, okay? 25. It's due October 15th. So here you go. Not on 8. 8 is the exam, right? If you have the exam on 8, yeah, it's gonna be due on the 15th. Okay. One more student coming. Okay, so here you go. The little table on the building blocks of physics, right? Building block of physics. Building blocks of physics. Okay, we are looking at the basic quantities, length, time, and mass. There are four more, which we are going to discuss in more detail later on. The primary definition, the position, right, that we have been talking about, and there is this other primary definition, that's force. Force is a push or a pull. And that's going to be the concept that we're going to concentrate now. The unit for the force is the meter, and it's not the meter. The unit for the force is the Newton, which is a combination of mass and acceleration. Okay, that's the Newton is a unit that involves the kilogram, the meter, and the second square. And this unit here comes exactly from one of the Newton's law. And we didn't talk about the law yet, any of the laws of physics yet, but we are going to start talking about them right now. Don't forget the forces. That's a very good way of defining force. Is either a push or a pull. And this idea of force has been around since antiquity, but the Newton's law that we're going to discuss today came about only in the 18th century, 16th, 18th, 17th, 18th century, during the time of Newton. Okay, this is the idea of force is a tried and tested idea that works very well, has been around a long time. It's just the law that involves force that came much later on, more than 1,000 years, almost 2,000 years later. Okay, so what you have to know, and you already know that force is a vector. Consequently, your push and your pull is going to have a direction and magnitude. And there are many types of forces out there. You have to memorize them. The most important one that you have to know is the force of gravity. Because list of forces. The most important force is the force of gravity, also referred as the weight. Okay, this is a and by the way, let me put, before we talk about the list of forces, just keep in mind that there are two types of forces, contact and non-contact forces. Okay, a push sometimes involve a contact, your finger, in order to push a block, it has to be in contact with this block. But then there are some very few forces. Okay, let me write it down here. Most of the forces are contact forces. There are very few non-contact forces. Non-contact for very few. And we're going to talk about that. And one of the most important forces that is also a non-contact force is the weight. Force of gravity, a non-contact force. Non-contact force. Okay, you should be familiar with the weight. Okay, if I, at this very moment, for instance, I'm exerting a force in this object. Let's say I'm exerting a force in my power pack. Here you go. This one better, right? My force, I am exerting a contact force in my power pack. This contact force is exerted by my hand, and it is an upward force. But in addition to this upward force, we also have another force, which is the weight of the power pack. Is the force that the Earth exerts on this object. This force is towards the center of the Earth, and the Earth does not have to be in physical contact with this object. An object can be floating or falling in the air, and the Earth is exerting a force on it. Okay, that's the importance of this force. Is always there. The weight is due to the attraction. Let's see, is the force of attraction that the Earth exerts on the object. Okay, every object that has a mass can exert this force. However, this force becomes only important in the vicinity of very large masses, like the mass of a planet, for instance. Okay, so that's the first force that we have. Keep in mind in graphical terms. Let's see here. Do I have? It doesn't look like I have the right slides here. Yeah, we need. Oh yeah, here you go. This is this one here. Okay, we have a mass that's above the Earth's surface. Let me draw the Earth's surface right here. Okay, and here is the non-contact force of the weight. This weight is given by the mass times the acceleration of gravity. And this weight is valid for any planet, okay? Any planet exerts this type of force in the object. The only thing that changes is the acceleration of gravity nearby the surface of the planet. M is the mass of the object, not the mass of the planet. Let me write that down here. M, here you go, is the mass of the object that's being subjected to this force. Okay, here's the let's write down Earth's surface. Earth's surface. And let's write that down there at the top, non-contact force. Non-contact force. That's the first one that you have to memorize. Okay? Non-contact. There are others. There are other non-contact force. For instance, examples of non-contact force, right? Examples of non-contact force. One, the weight. Okay? Another force, another non-contact force is the magnetic force. Everybody has worked with these magnets. And that's going to be covered in Physics 7. But before covering magnetic force, we cover another force called the electric force, also in Physics 7. Okay, is the force that an electric charge exerts in another electric charge. Here, the weight is the force that a mass exerts in another mass. The weight is a force that is related to the mass of the object. Any massive object exerts a force in another one. However, these forces start to become measurable only if you have a very large mass, like a planetary mass. Okay? Yeah, let's write it down. This force starts to become non-negligible, right? Negligible. One minute, there's a little emergency here. Yeah. Okay, I'm back here. Emergency resolved. Okay, the weight is the force that a mass exerts in another mass. These forces start to become non-negligible only when one of the masses is very large in the planetary scale. Okay, on the order of a planet, on the order of a planetary. Okay, scale, at least, right? The moon exerts, let's say, on the order of, okay, let's put it this way, planetary scale. Let's take a look at the moon, for instance. The moon is not a planet, but it does exert a non-negligible force, non-negligible weight. Okay, but let's look at the mass of the moon, for instance. Here you go. That's the mass of the moon. 10 to 22 kilograms. Very large. Okay. In the case of the mass, at least, on the order of 10 to 22 kilograms for the case of our moon. The case of our moon, here you go. Superscript, okay? Then we have the electric force, the force that an electric charge exerts in another electric charge. You have a magnetic force, physics 7 as well. The force that an electric current exerts in a charge at motion. Then we have fancier non-contact forces that we won't be able to cover, but it's important that you know. We have the strong force, which is a nuclear force, strong force, the nuclear force. And we have the weak force, which is also a nuclear force. Those two forces were discovered only in the 20th century. It's recent stuff. Okay, so let's just concentrate on this non-contact force. The weight, given a mass m subjected to a gravitational acceleration g of a planet, okay? The weight of this mass will be given by, here you go, weight equal to m times g. Okay, so for a 1 kilogram mass nearby the surface of the planet Earth, right? Planet Earth, comma, its weight will be given by approximately 10 newtons. 1 kilogram times 10 meters per second square, right? Will be given by, let's put here, weight, 1 kilogram times 10 meters per second square, which is equal to 10 meters. Remember, I'm doing an approximation here. And it's not a bad approximation. It's a very good approximation. It's within 2% of its actual value. Okay. On the surface of the moon, on the okay, this force and this force, here you go, one more thing. And this force is directed towards the center of the planet Earth. Okay? How long do we know about this force, right? let's see here, history of the weight. Let's take a look here. If let's say like if Google has history of weight, has any, here you go. The history of weight measurement began in early civilizations, 8,000 BC. See that? So has been a long time. This idea of the weight has been around for a long time, evolving from body-derived units like the cubit and foot to standardized scales and weights used for trade and construction by 3000 BC in cultures in the Indus Valley, Babylonians and the Egyptians. Okay. So, like I said, the idea of force has been around since antiquity, and consequently the idea of weight as well. People has been aware of this important force since at least 8,000 BC. Since at least 8,000 BC. Okay. Now, what the ancients didn't know is that if you're nearby the surface of the moon, you also subjected to the weight, a different type of weight. Okay. On the surface of the moon, an object would also be subjected to a weight as well, albeit small, right? Although smaller than the one on Earth. The weight on the surface of the moon is approximately 1/6 of that of the Earth. Okay, and let's write it down. It varies from planet to planet, from Jupiter, Mars, Saturn, even the Sun exerts a weight on the objects nearby it, especially the planets. Here you go. Weight on the surface of the moon is going to be 1/6 that of the weight of the Earth. So 10 divided by 6 is going to be approximately almost 2. You can do the math, right? 10 divided by 6, a 1 kilogram mass, 1.666 newtons, 1.67 newtons. Okay? On the surface of the moon. On the surface, let me emphasize that. And then the other planets and the sun also exert a force on objects nearby them. Okay, so that's the first force that you must know. Don't memorize this equation. In order to know the weight of an object on the surface of Mars, you have to know the acceleration of gravity on the surface of Mars. In order to know the weight of the object on the surface of Venus, you must know the acceleration of gravity on the surface of Venus, which is almost the same as that of the Earth, because Venus is very similar in mass to Earth. It's slightly smaller only. And so on. Okay. Other forces. Okay. That is one, normal force. Let's start with the normal force. Okay. An object, for instance, this object right in here, let me do 2 slides here. I'm going to, I don't want to. An object here at the bottom of this depression, okay, is subjected not just to the weight, to attractive weight of the Earth, but is also subject to a contact force that we call the normal. We call it a normal because it makes an angle of 90 degrees with respect to the tangent. Okay, that's what the definition of normal is all about. Something that makes an angle of 90 degrees with respect to the tangent to the surface. That's the most generic way of illustrating this normal force. We can illustrate in a simpler way as well. I'm going to illustrate it in a simpler way now. Here on the surface, on this planar surface, okay? On this planar surface, here on this planar surface, the normal force, again, is going to be perpendicular to the tangent to the surface. The tangent to this surface here coincides with the surface itself, okay? But not here, in the case of this depression. Okay, let me simplify this drawing, right? That's the first one I should know. That should show you, right? Normal force here, and then there is another normal force here at the bottom of this depression. And then there is another normal force here. If this object is placed right in here, okay, you are going to have a different normal force, a different value of the normal force. Okay, this normal force will coincide with this normal force. The value of this normal force here will coincide with the value of this normal force, but not with the value of this normal force here. Not because the direction is different, right? Not only the direction is different, but also the numeric value may be different as well. Okay. Here's the slide for the weight, right? And here you go, the object over the surface of the Earth. We have the weight, and we also have the normal, right? Exactly the same as you saw there. And this object is at rest. And what you have right in here is what we call the free body diagram. A free body diagram is a diagram in which we document all the forces that an object is subjected to. So in this case, we have the weight and we have the normal. Weight and normal. Okay. Remember, this free body diagram is very important. Free body diagrams are very important. Every problem in physics that deals with force, we will need to use a free body diagram. There you go. Same normal force that you saw before. The weight, but now, if the object is touching the wall, right? A wall, like in this case, the object is at rest. Suppose that I decide to apply another contact force with my own hand. This is my hand, okay? This is my hand. And I call this force normal number 2. My hand. Doesn't look like, right? My hand. Applying a normal force 2. And the object is at rest. The wall must exert a force as well to counter this other force here. Okay? And so here you go. We're going to have this third normal force. First normal force, second normal force due to my hand, and a third normal force that the wall is applying. If there is no force applied from the left to the right here in this object, the wall will not exert any force whatsoever. There will be a contact, yeah, but there will be no force. But there will be no contact force. You may have a contact there with the wall, but the contact force is going to be 0, okay? So let's write that down, all of that. Normal force at perpendicular to the tangent to a surface. Okay. Examples. Okay. An object resting over a flat surface is subjected to an upward normal force that counters instead of flat surface, horizontal surface, right? An object resting over a horizontal surface is subject to an upward normal force that counters the weight. Okay. If you touch an object with your hand, if you touch an object with your hand, you also apply a normal force to this object. The normal force doesn't have to be in the vertical or upwards. Okay? If you touch an object with your hand, you also apply normal force to this object. If you compress an object towards a wall, right? The wall will also towards a vertical wall. Let's put it this way, vertical wall. The wall will also exert a normal force on the object, which will be in the horizontal direction. And so on. And so on, right? Let's go back to that. Let's see. Let's give another example. The one that is in that depression, right? The circular depression is an interesting example. This one right in here. Okay. An object sitting at the bottom of a circular, don't forget circular depression, will exert, will be subjected to an upward normal force from the depression. An object sitting along, let's say, an object sitting anywhere in a circular depression will be subjected to a normal force that is perpendicular to the tangent to the circular surface. And so on, right? There are many other examples, but let's stick with the normal force and the weight for now. There'll be other forces, okay? As we move along, I will introduce you to those other forces. Go. Example, here you go. If an object is at rest, and now what do I do here? I attached a string to this object, okay? Attached a string to this object, but this string is loose. Consequently, this string is not exerting any force on the object whatsoever. And my free body diagram will be this one that you see right in here. Weight and normal force. And I specifically stating that the object is at rest. There's a reason for that, okay? Which will become apparent soon. Oops. Next, now I decide to stretch my string, okay? I decide to stretch my string. Now, this object is subjected to a tension. The name of this force is tension. This tension can be in any direction you want. Horizontal, vertical, a combination of horizontal and vertical, okay? Tension. So let's document here tension, force. A force applied by a string that is stretched, right? This force can be in any direction. Horizontal, vertical, or a combination thereof. Combination thereof, okay? If I were to illustrate this tension, we go other direction of the tension, right? Here you go. I can put this tension at an angle, okay? I can place this tension downwards as well. I can even use a string to try to suspend the object. Okay, that's my velocity here, T for tension. But going back to this case here, okay, going back to this case here, if we apply a tension here to this string in the horizontal direction, this object will tend to move unless there is another force countering this tension. Okay. If we apply, consider, here you go, let's write it down. Example, right? Consider an object sitting over a horizontal surface. If we apply a tension, horizontal tension, and attach it to a string, right? And attach it to a string. If we apply horizontal tension to this object, the object will tend to move unless there is another force countering the tension. Okay? Countering the tension. Okay, in this illustration here you go. If after applying a tension the object, tension, and the object still remains at rest. This means that there is another force countering it. This force is usually the force of friction. The force of friction, another contact force. Okay, so let's put here force of friction, another contact force. And that's what this illustration is all about. Have you ever done this experiment before? Okay, it's not difficult to make it. Okay, here you go. Here's my cell phone sitting in horizontal surface, right? Now, at this very moment, you can already visualize that there is a weight being applied to my cell phone and a contact surface, a contact force called the normal due to the cover of my book, right? But if I now apply horizontal force, it can be a string that I stretch it. Let me put it upside down. Here goes better. If I apply horizontal force, can be a string or can be even this normal force, and my object and my cell phone doesn't move, it means that there is another force countering this contact force of mine. And this other force is usually, if I don't say anything else, right? If I don't say anything else, this force must be the force of friction. And even better, there are two types of forces of friction. If the object is at rest, the force of friction would be the static force friction. Okay? The static force friction. Let's write it down, force of friction. There are two types of force of friction. A, static friction, and kinetic or dynamic friction. Static friction if the object is at rest. If the object is at rest, okay? Kinetic friction if the object is moving at rest with respect to the surface where it sits, okay? Where it sits, right? Is moving also with respect to the surface where it sits. So you already have three different contact forces. Other forces, contact. There are more, but let's see, that's what you need so far. I don't want to overwhelm you with that. Okay, here you go. Tension, right? I'm applying a tension. If the object stay at rest, it means that we have a force of static friction. And I made sure that this force of static friction, see, it must have the same length as the tension, right? Here you go. Just to make it realistic enough. This force of static friction is actually occur right here at the surface, between the object and the surface itself, okay? Let's make it thicker. Yeah, better. Force of static friction. Let's make all this force thicker so they look better. Can't, huh? Like that. Like that. and this one. Like that, okay? So get used to those diagrams, free body diagram. Okay, example, here you go. Another example here. Tension at an angle. If the object at rest, it means that this component of the force of static friction it means that the force of static friction must be equal to this component of the tension, okay? Makes sense, here you go. And that's where the whole idea of Newton's law comes into place. It goes sent to back like that. Okay, here you go. Again, I'm doing the best to display a realistic length for this force of static friction. But because this tension here is also has a vertical component, it's also going to affect my normal, okay? Because now, you go, my tension, I'm gonna draw the components of this force. Now do you understand why it's important to study vectors? You go, let's see. I want, no, I couldn't do it. Let's see, format shape. And the other one, good. Has this horizontal component, and it must also have a vertical component, right? I'm gonna take out this dash. And shrink a little bit. Yeah. Shrink a little bit. Oops. Dash it. Dash, dash, dash. Like that. Like that. Dashes. Like that. Huh? Let me change the tip of my arrow. Better, right? Here you go. T. That's the T. The tension force. That's going to be the Y component of the tension. And the other is going to be the X component of the tension. The X component of the tension, okay? Okay. And because now my tension has a vertical component, it means that it will affect the normal here, okay? Instead of this huge normal that has the same length of the weight, now the normal is going to have a shorter length. Do you get that? Okay, here you go. This length plus this length here must be equal to this length here. And that's one of the first laws of physics. Okay? The Newton's law of motion, first Newton's law of motion. Now we can introduce you the first Newton's law of motion, now that we have all those ideas of force. First Newton law of motion. And then I'm going to say first part. First part. First Newton laws of motion has two parts, the first and the second. Let's look at the first part. First Newton's law of motion has two parts. The first part is the following. First part. If an object is moving, is at rest, comma, the net force applied to this object is zero. Okay? Think about that. And I want to have an earlier break now. Okay? While you think about it. And 2:34, not 2, it's 10:34. 10:34 a.m. break. 10:34 to 10:49. Okay. Let's take a break now, and we will. In this meantime, you think about that. That the first law you're being introduced to, Newton's first law of motion. Okay. So I see you in 15 minutes. I'm back here. Let's share the screen. Okay, first part of Newton's law. If an object is at rest, the net force applied to this object is zero. Okay, so mathematically, we can express like the following. Okay. Remember, it's the net force. It's not just a single force, but it's the net force. Mathematically, we can express like that. Here we go. If an object is at rest and v equal to zero, right? Then the net force applied to this object is going to be zero. So here you go. Here's the summation, right? And the net force means force 1 plus force 2 plus force 3 plus force 4 until force n. The summation, the vectorial summation of all those forces is going to be equal to zero. Okay? For the, here you go. Let's start with the simplest case, right? Simplest example. Here you go. is one right in here. You go. Examples. Don't forget the objects at rest. Example. Example. You know? Oh, this one is supposed to be elsewhere. Right in here. Example. Formulate Newton's first law of motion. Formulate, here you go, the first part, right? The first part of Newton's first law of motion. For the case illustrated below. Okay? So here you go. Solution. That's assuming that we know the weight and the norm and the mass of the object. Okay, from the first part of Newton's first law. For the case, the object for the object of mass m below, formulate the first part of Newton's first law of motion. There you go, like that. We have only two forces. We have only two forces, normal and weight. Consequently, Newton's first law of motion can be written as, I'm gonna use this guy here. Here you go. Net force is going to be F1 plus F2, right? Let me put that on the side. N is equal to, N is equal to 2. Doing it step by step, right? F1 plus F2, only two forces. Let's say F1 is going to be the weight. And I'm going to use the vectorial notation. Here you go. F2 is going to be the normal. Okay. Equal to 0. Both forces are on the vertical direction. So we can go ahead and writing that down here. Here you go. mg. mg is going to be in the negative y hat direction. The normal force is going to be on the positive direction. So we can put positive here. And that's, oh, what did I do here? That's the one I want. Okay, copy and paste. Here you go. We can go another step here. Negative mg. Like that. Negative mgy. And that's how we formulate Newton's first law of motion using what we know, right? I can even invert the order here. to save on the number of symbols. You know? And then here you go. Now, second part of this problem. Find the value of the normal force in terms of mg, right? So that's another example. Example 2. Find the value of normal force in terms of mg. Okay, solution. Here you go. We start with this equation, right? That we formulate from Newton's law of motion. Here you go. We pass the mg to the other side. I don't need the y hat vector anymore. And that's the value of the normal force for this specific situation. For this specific situation. Okay. Now let's forces so far, right? Forces so far. Here you go. 1, weight. I introduced you to the weight. I introduced you to the normal force. I introduced you to the tension. I introduced you to the force of friction. In reality, we have two forces of friction, right? Force of static friction and force of kinetic friction. I didn't introduce you to force of kinetic friction yet, but at this point in time, you should know those forces. So now it's just a matter of solving different problems, okay? Let's take a look at this other example here that I illustrated for you. That's example 3. An object is at rest on a horizontal surface and being pulled by a string of tension T, making an angle theta with the horizontal, okay? The first thing that, here you go. Why did J? Here you go. Good. What's the value of the net force? 2. How many forces are being applied to the object? 3. What is the vectorial relation between these forces? 4. You write your vectorial equation into 2 scalar equations. That's a more complicated problem now. The first problem is just a one-dimensional problem. The previous example, right? The previous example is just the one-dimensional problem. Okay. The previous example is just a one-dimensional example along the vertical direction, Now we will deal with a 2D example. Forces along the vertical and horizontal directions. Objects at rest. Okay, solution. What's the value of the net force? on. Why keep on saying J here? So odd. Okay, because the object is at rest according to Newton's first law. Newton's first law of motion, comma, the net force must be zero. Zero, okay? So we can rewrite that. Here you go, like this one. Net force must be zero. That's first item of the problem. Oh, of the example. Here you go. Now, second. What am I asking the second one? How many forces are being applied to the object, right? So all I told you, the objects that rest on horizontal force on horizontal surface and being pulled by a string of tension T, making an angle with the horizontal. Okay, so the weight must be there. The weight. Here you go. We mentioned that there is a string applying attention to the object. That's one force, first force. Okay, two. Forces applied. Let's put this way. Yeah, here you go. Better now. Better organized now. C. Since the object is at rest, comma, we must have another horizontal. Let's see. We mentioned that there is a string applying attention to the object. Okay, yeah. Since the object at rest, we must have another horizontal force countering the X component of the tension. This force must be the force of static friction, F sub S. Here you go. T, right? F sub S, like that. And let me illustrate also, right? How it looks like. It looks, according to the description of problem, is exactly something like that. Okay? There's an angle theta, right? Let me get the angle theta here. Here you go. It's exactly something like that. The problem, let's see, the problem tells you only that. That's what the problem tells you. Okay? But you do know that the object at rest, because the object at rest, the net force along the x direction must be equal to zero. So there must be a, here you go, problem. Let's see here. Example, right? Example. That's what I tell you, right? Because the object is at rest, there must be a X component, there must be a frictional force countering this object. And because the object is at rest as well, this frictional force must be the static force of friction. Let's see if it's, yeah, that's right. That's my second force. Okay. There is a force that's always there, and the force that is always there is what? Is the weight. Always there is the weight. The normal is not necessarily there because there must be a contact. If there is no contact, right, the object is just free falling, like during this interval here. Okay, there is no normal force while the object is free falling. But because this object is in contact with the ground, there must be a normal force. So there's a total of 4 forces. 1, 2, 3, 4. Okay. And I'm going to do something else here. Here you go. Like that. Like that. That's what the problem told us. And let's do it. Let's see. An object. Let's put here of mass m. Okay. So we is at rest on a surface, horizontal surface, and being pulled by a string of tension T, making an angle theta with the horizontal. That's the information that we have. And let me put the mass of the object here as well. Here you go. Here you go. Copy and paste there. Oh, no. Let's try it again. Here you go. Okay. The problem in a pictorial sense, right? The problem provides you, right, with the following information. Here you go. Here you go. That's what? The mass, the tension, the angle, and the object at rest. Okay? Because the object is at rest, according to Newton's first law of motion, net force must be 0. Okay? Forces applied. How many forces are applied to the object? Okay? We mentioned that there's a string applying a tension to the object. First force, tension. And in a pictorial sense, we can like that. And write down like that. Even better, let's put the mass here, right? Again. In a pictorial sense, the tension has an x and y component, x and y components. Okay. Since the object is at rest, it must have a force that counters the x component of the tension. And we can, that's what this illustration is all about. There you go. So let's illustrate that as well. Here you go. Okay. A third force that's always there, that is always there, is the weight, right? Here you go. And I'm going to illustrate this third force. Here you go. The weight. Do I get rid of this thing here? Huh. Okay. And finally, since the object is also at rest, we must have a normal force upwards. Finally, we must have a normal force to cancel out the weight. So those are consequently, we have a total of 4 forces. Consequently, we must have a total of 4 forces. Next, 3. What's the vectorial relation between these forces? Oh, okay, you saw that before, right? Here you go. I'm gonna look at this. Take a look at this equation here. Here you go. Oops. Net force. Total of 4 forces, so you have to change here to 4. F1 plus F2 plus F3 plus F4. F3 plus F4. Okay. The first force is the tension. Oops. Tension. Oops. Tension. The other force is the force of static friction. and I abbreviate by S sub S. The third force that I mentioned was the weight. The last force is the normal. Here you go. Okay, and here you go. That's how we formulate Newton's law of motion. Here you go. What's the vectorial relation between these forces? Okay. 1, 2, 3. Here you go. That's the vectorial relation between these forces. Here you go. These forces. Item 4. Here, write our vectorial force into two scalar equations. Okay. How do we do that? Okay. Here, write the above in terms of two scalar equations. Two scalar equation means in terms of its x and y components. Okay, that's what we have to do here. So here you go. The tension has both an x and y component, so we're gonna put it T sub x. The force of static friction has only a x component in the negative x direction, right? The weight has only a y component, and the normal has only a y component. Okay. And then, oh, here you go. Since the weight has only a y component, the x component of the weight is 0. Since the n has just a y component, the y component of the normal is 0 as well. Okay. And here you go. The second equation, y component of the tension. Force of static friction doesn't have a y component. The weight has a y component. The normal has a y component. So here you go. That single vectorial equation can be written down into two scalar equations. And now let's simplify that. Okay, here you go. Can we do better? Yes, we can do better. You know, we can here write like in terms of the modules. We can, you know, the x component of the tension is along the horizontal, the positive horizontal direction. Consequently, we can write that down in terms of a modulus of Tx. Okay? If we do the same for the force of static friction, we gotta put a negative sign here. Remember, the modulus means a positive value, right? So if we put a modulus here, magnitude, right? We have, oh, not here, like that. We have to put a negative sign here because it's along the negative x direction. The same thing applies for the y component of the tension for this specific problem, right? The weight is downwards, consequently can be here written in terms of minus mg, and the normal is along the positive direction. So we can emphasize this fact by writing those equations, these two equations in this way. Do we have more? We don't need more. Okay. So that's the first part of the problem. Oh, we can do one more thing here, right? We can write that down in terms of the angle. The T sub x can be written down in terms of modulus of the vector t times cosine. Dt sub y can be written down modulus of t sine of y, sine of theta. This one should go downstairs here. Okay. Is a level higher in difficulty, this problem. 322, we can, not 322, it's 11, right? 23, yeah. Let's go a little bit more, let's see. Okay, so that's the first part of Newton's first law of motion. Okay, let's look at the second part. Second part of Newton's first law. Newton's first law. First part, object must be at rest. Second part, object is moving with constant velocity. That's the second part. Okay. In this specific case, because the object is moving with constant velocity, it means that the acceleration is equal to 0, right? If the acceleration is equal to 0 here in the second part, the acceleration also must be equal to 0 in the first part because the object is at rest. Do you see what's common to those two parts? What's common to those two parts is the acceleration. Is the acceleration, not just the acceleration, but the fact that the net force is going to be equal to 0. So that's what's common to those two parts of Newton's first law of motion. Okay, so now we can illustrate the same thing that we did here for object at rest. We can do for an object moving with constant velocity. Okay. Can do the same thing for object moving with constant velocity. And here is a case in which the object is moving from the right to the left. And when I meant V, I meant magnitude of V, okay? The object is moving from the right to the left. And now we have a tension to the left. And because the object is moving, the force of friction is going to be the force of kinetic friction. Okay? Here's an example of this case. Consider the case. Consider, for instance, the case of an object moving with constant velocity while being, pulled from the right to the left by a string, right? In this case, okay, second part, object moving with constant velocity. Net force is still 0, okay? In this case, the net force is also 0. Also 0. And we have the following consequences. Consequences. 1, we must have a force of kinetic friction from the left to the right. To the right. Okay. Second part, and let me put that in. You go like that. Second part, object is moving with constant velocity, net force is still zero. Here you go. I'm gonna put it summation of all forces, right? 1, 2, 3 plus Fn equal to zero. You go like that. And I'm going to do step by step here as well. Oops, not here. So this one, I'm gonna erase all of that stuff. That's what we know about the problem, right? Constant velocity, v greater than zero equal to constant. That's okay. Which implies the acceleration is equal to zero. Which implies A is equal to zero. Here you go. Angle theta. Because the object is moving with constant velocity and the acceleration is equal to zero, the net force is going to be zero. Because the net force is equal to zero, the component along the x direction, there will be a component along the x direction that's going to counter the x component of the tension. Okay, so, and this component that counters the tension is going to be the force of kinetic friction. Is kinetic friction because the object is moving. In addition to these two forces, there must be a third force that's always there. And this third force is the weight. Okay? And because we have a contact of the block with this flat surface, with this horizontal surface, we must also have a normal force. Here you go. Oops. A normal force. This normal force must be smaller, right? Let's make it because of the y component of the tension. Grid line looks like this thing here is a little bit off. Yeah, better now. Good. That's why it's nice to have grid lines here. Did you get the idea? Okay, so now we can combine those two parts into a single law. Okay, the two laws combined, the two parts of the law combined into a single one. Okay, oh, I gotta finish this one, right? We must have a force of kinetic friction from the left to right because the object is in motion. The object is in motion. 2, the force that is always there is the weight. 3, because the object is in contact with the surface, we must also have a normal force, okay? And I'm going to get all this illustration. All of that is going to be illustrated. in this picture. Here you go. Like that. And now we combine those two parts. We combat by combining the two parts of this law. We can reformulate it as, right? Newton's first law of motion. If an object is at rest or moving with constant velocity, then the net force applied to this object is zero. And the converse is also true. And the converse is also true. And the converse is also true. If the net force applied to an object is zero, the object will be either at rest or moving with constant velocity. Okay? It's going to be either or the other. Either one or the other. So that's how we formulate Newton's first law of motion. Okay. And now, let's see, did I put, yeah, net force is equal to zero. Good. I put it here, so we have it. That's the static part. That's the static case of Newton. Okay. So let's repeat the forces that we have so far, so you don't forget about them. Like I said, there are more. There are more that will be introduced at the right moment. Here you go. Force of static friction, right? Force of kinetic friction. Force of friction. Static friction, kinetic friction. Okay. Here you go. And then there are other important problems too that becomes a little bit more difficult to solve. But here you go, this case, for instance. Okay? An object at rest on the top of the inclined plane. Let me illustrate it with as little information as possible. Here is the plane. I want to see my grid line. Let's see. Yeah, good. Horizontal. Let me erase my grid line. And go. So let's say we have a tension force applied to this object. And because the object now lies in a inclined plane, something changes slightly. Let me get let's see. Let me put that right here. Yeah, here you go. And I will name that. Let me name that inclined plane angle theta. And on the top of that, we have a tension being applied to the block as well in the uphill direction. But this tension makes an angle, a different angle, not the same angle, theta, but let's say a theta 1 angle. Ooh. Theta 1 angle. Like that. This is a little bit more complicated problem, okay? Because now you have to deal with inclined planes. And when you deal with the inclined planes, the components of the weight is going to change, okay? The weight is no longer going to be perpendicular to this plane. Okay. So let's so here you go. Example. Going back to my another example, another more complicated example. Consider an object of mass m at rest on the top of an inclined plane, making a known angle theta with the horizontal. Theta with the horizontal. In addition to the regular forces, we also have two additional forces. A tension that I'm telling you, okay, that makes an angle theta 1 with the horizontal, not with the surface of the plane. And a normal force on the left side of the block. On the left side of the block, we call it normal 2. Okay. Then we repeat what we did before. What's the value of the net force? How many forces are being applied to the object? And what are these forces? What's the vectorial relation? And you write our vectorial equations, two scalar equations, okay? So let's write down here the solution. But first, let's illustrate, right? Here you go. What the problem is telling us is that we have this normal force here that I call M2. So let's add right here. Those two forces plus the regular ones. Okay, this normal force can be my hand that's propelling the object, that's helping the tension, right? That's helping helping the block not to slide downhill. Okay, so here you go. What are the forces that are there? Okay, first the weight. The weight is always there. Here you go. In addition to the weight, we must have also a normal force, right? A normal force, and don't forget, now the normal force is no longer in the vertical, but it's going to be making an angle with the vertical because we have an inclined plane. Do you understand the difference between this problem here and the previous one? Right? As the plane becomes inclined, the normal changes direction. This normal here, right, between the surface and the block changes direction. As long as a given force of my hand helping propel the block, Okay, and since the block tends to slide down this plane, right, tends to slide down this plane, or even better, if the block tends to slide down the plane, the force of static friction would be upwards, okay? But because we have those two forces uphill, it means that the block tends to climb uphill. If the block tends to climb uphill, the force of static friction must be downhill, okay? If we didn't have those two forces here, the tension and the normal, the block would tend to slide downhill, yes. But because we have those two forces here, they may be overcoming the x component of the weight. For this reason, we must have a force of static friction that's downhill. Okay, so here we go. And let's see, here you go. Copy this one and paste it. Here you go. If the block tends to slide uphill because of those two forces, then we must have this force of static friction downhill. Okay, so let's document all of that here. Solution. What the net force you already know, right? There is no net force is equal to 0. Object is at rest, because the object is at rest, okay, net force is equal to 0. Because object is at rest, the net force must be 0. How many forces are applied to the object? Okay. Forces applied to the object. 1, tension, which was given. Normal, which was also given. 3, weight, which is always there. 4, another normal force due to the surface where the object rests. Okay. And 5, right? 1, 2, 3, 4, 5. Since the object tends to slide uphill because of the tension and the other normal force, we must also have a force of static friction that goes downhill. Okay. And now we can go ahead and copy all that stuff here. I don't want this one. Let's use this one instead. This one. Less messy, right, than the other. Like that. Copy and paste. See below, right? There's something missing here. Yeah, there's an angle missing here. Yeah, that's the one I want to copy. Okay. Copy and paste. Here you go. Now it's better. Okay. What's the vectorial relation between these forces? Okay, so 5 different forces. Here you go, net force 1 through 5. Force 1 is the tension. Oh, no, not here. Force 1 here is the tension. Force 2 is the normal number 2. I'm calling it number 2 because we have the normal number 1, right? That's always there. Force 3 is going to be my weight. Force 4 is going to be my normal number 1. Just change the subscript. And force number 5 is going to be the force of static friction. Like that. And then we can break it down into 2 scalar equations. Okay, breaking the above down into 2 scalar equations. We get, okay, the tension is going to have an x and y component. X and y components, right? Which other force? The normal 2 is also going to have x and y components. And that's going to be x component in this case. The weight has only a y component. Let's see, I'm going to put it y prime, okay? Let's see. Horizontal and vertical component. Instead of x and y component, let's write that down in terms of horizontal and vertical component, okay? The weight has no horizontal component. Normal 1 is going to have both horizontal and vertical components, right? You can see, right? Normal 1 has a horizontal and vertical component. And the force of static friction is also going to have a horizontal and vertical components. Like that. Let's write down H. Yeah. And then we're going to have, you know, the vertical component of the tension, the vertical component of the second normal, the vertical component of the weight, the vertical component of the first normal, and the vertical component of the force of static friction. Okay? Here we're writing in terms of the horizontal and vertical components. But what if we want to write in terms of the X and Y component according to this frame of reference, okay? See, the X axis makes an angle of theta with the horizontal, okay? What's gonna happen to my equation? My equation changes slightly. We are going to have the X component of the tension and the Y component of the tension. We are going to have only the X component of the second normal, and the Y component of the second normal is going to be 0, because this normal here is only parallel to the X-axis. See that? The X component, the weight is going to have an X component, okay? The weight now is going to have an X component because I am using a different frame of reference, a different axis. Going back here you go. See that? The weight is gonna have this X component here. And it's going to have a Y component as well. The normal number 1 is not going to have a X component, right? The X component of normal number 1 is going to be 0. And normal 1, the Y component is going to be equal to normal 1. And finally, the force of static friction is going to have only an X component, but it's not going to have any Y component whatsoever. Here you go. And we can here write, simplify that. Here you go. The normal 2 has only an X component, so we can write down as a normal 2. Wx is going to be mg. Don't forget this is in the negative direction, right? Mg, which angle is that going to be? Let's see here. This angle is theta. Okay, so it's going to be mg sine of theta. Sine of theta. Normal 1. Normal 1 doesn't have any X component whatsoever. And the force of static friction can be written down like that. The Y component, let's see, here the mg is going to be in the negative Y direction as well. So it should be minus mg cosine of theta. The Y component of the normal, let's see here. Oh, here I gotta change too, because the normal has only a Y component, so this Y here becomes unnecessary. And here you go. We can eliminate that as well. Make as simple as possible. Okay, so here you go. We can here write the tension, the X component of the tension in terms of its cosine and sine, right? That's theta, but that's going to be theta 1, right? Theta 1. And it's a positive, the positive direction. The normal is going to be in the positive direction as well. So I'm going to emphasize it here. That is, this number is a positive number. Here I already wrote down. M is positive, G is always positive. The force of static friction, I'm going to emphasize that it is a negative number. Okay, because it goes against the X-axis, goes downhill. Consequently, this is negative. Here you go, the Y component is going to be just like the x component, but instead of cosine, it's going to be sine. Okay. The mg already have it. And one, yeah, okay. And all I have to do here is to put in terms of the magnitude. N1. X and Y components. 357, 357, 1157, right? Yeah, 1157, time for our break. Get used to that, okay, folks? Get used to that. There will be problems like that you have to solve. And I need to elaborate on the forces of static and kinetic friction as well. Let's see if I have it here. 2 more minutes to go. Let's wait 2 more minutes, and so we go for a break. Okay, example 1, example 2. I have better, right? Better illustrations here. You go. Yeah, that's what I want to do next. Force of static friction. Those slides are better. Okay. Any questions? Am I missing any chat messages from you? Okay, so we are set for the exam the day after tomorrow. Just to make sure that you're ready. Okay. Exam 1 the day after tomorrow. Okay. Chapters 1 and 2. Chapters 1 and 2 minus the chapter 1 minus the vector, right? And chapter 2. We leave the vector saying for the next, for the exam number 2. Let's not forget exam starts at 9:40 a.m. October 8th and finishes 11:40 a.m. Okay. After submitting your exam, you may leave. Submitting your exam, you may leave. What else you have? Make sure you use the restroom before starting the exam. Okay. So let's see. 12 noon right now. Break. 12 noon to 12:15 p.m. Okay. See you in 15 minutes. Okay, we're back here. And let's see what we have done so far in the book. Let's compare what we did here in the class and where the book is with respect to how do I instructors? Login. Okay, that's the one we want. Book. Let's see here, chapter 4. Forces in Newton's law of motion. Concepts of force and mass. Okay, and I will. So far, we covered the following sections in the book. Okay. Concepts of force and mass. Okay, force is a push or a pull, and force is a push or a pull. Mass is a measure of the amount of matter an object has. That's the difference between one and the other, right? We cover Newton's first law of motion. We are going to start Newton's second law of motion, the vector nature of Newton's first and second law of motion. We already covered the vector nature of Newton's first law, right? Now we are going to cover the vector nature of Newton's second law of motion. We have Newton's third law of motion. We didn't cover yet. Types of forces. The gravitation. Let's take a look at the types of forces, right? How the book covered that. Types of forces, an overview. Yeah, see here, gravitational force, strong nuclear force, weak nuclear force, right, that I mentioned. You don't have to worry about those two, but you have to worry about this one. The gravitational force is the weight. And that's a very short chapter. There's nothing much here. Gravitational force. Okay, I didn't introduce that yet, but I just, gravitational force. I introduced only weight is equal to mg, but there is another part of the gravitational force that I didn't talk about yet, but I will. Normal force we covered. Static and kinetic frictional forces, I cover only part of it, not completely everything. The tension force, I covered. Equilibrium applications of Newton's law of motion, I did some examples. And then non-equilibrium. Equilibrium applications is whenever the net force is equal to 0, okay? Let's put here, net force equal to 0. Net force equal to 0. That's what equilibrium applications of Newton's law of motion is all about. And non-equilibrium has to do with Newton's second law. That's what we covered so far. 1, 2, 3, 4, 5, 6 out of 12, plus half of that, and let's say half of that as well. Okay, so so far we have covered more than half of the chapter. Now let's talk about Newton's second law of motion. Okay, and let me put this first law of motion. Newton's law, here you go. let's formulate Newton's law here. Newton's first law of motion. Okay, and if the acceleration, right? Another way of writing down Newton's first law of motion. Law of motion. If the acceleration of an object is 0, then the following apply. Okay. Net force is equal to 0. And acceleration equal to 0 means either object at rest or moving with constant velocity, right? Now, if Newton's second law of motion applies when the object is accelerated, or A is different of 0. Okay, so instead of net force equal to 0, now net force is going to be equal to mass times acceleration. Okay, like that. See the distinction between first law and second law? Actually, what you see right in here is just a special case of what you see right in here, right? Note, see, that the first law of motion, is actually a special case of the second law of motion. For this reason, it shouldn't be considered a law, but just a corollary. For this reason, the first law is not a law per se, but just a corollary or consequence of the second law. Okay? And let's see if here you go. I'm gonna give you some examples here, right? Here one example of the second law of motion. An object subject just to the weight, okay, is actually accelerated, where the acceleration is equal to the acceleration of gravity. Have you thought about that? F, net force example, right? Example of second law of motion. Simplest example of the second law of motion. Simplest example of the second law of motion. An object subjected only to the weight. Okay, and here's an illustration of this object subjected just to the weight. Net force is equal to the weight. Okay, net force is equal to the weight. Here we go. Using Newton's second law of motion for this case is going to be, here we go. This is a one-dimensional problem. Okay. Net force is equal to the weight. And the weight, let's not forget, is minus mg downwards. It's minus because the weight is downwards, right? The right way of doing that is like that. Net force. Oh, gosh. Equal. I'm going to do another step here. That is just one force. N is equal to 1. Net force is equal to the weight. Weight is minus mg y hat. And that is equal to mass times acceleration. Simplest example you ever see applying Newton's second law of motion. Okay, so if you want to find out the acceleration of this object, all you have to do is to solve this equation that you see right in here, right? Mass cancel out with mass. And the acceleration is going to be equal to the acceleration of gravity, 10 meters per second squared, in the negative direction. Okay. If we can write that down in a scalar fashion, just like A equal to minus G. Okay. Or if you want to write that down in terms of the magnitude of the vector, just another way of writing the same thing. Which, by the way, is equal also to the magnitude of the scalar. Right? Because as a magnitude, we do not have a negative sign. We have just a positive number at the end. That's the simplest example that you ever see that uses Newton's second law of motion. We can have another one. Here you go. The case of the force of static friction. Okay, very important. Can cover that now. What happens with the force of static friction, right? The force of static friction is something that changes. The force of static friction doesn't have a single value. Doesn't have a single value. Okay, now we are talking about force of static friction. And then we get back to Newton's second law. Okay, first we need to cover that. The force of static friction is a force that does not have a single value. Okay? Instead, it has a range of values. And its value depends on the other forces. Okay? Let me give you an example. If an object is at rest, right? Consider an object at rest. And let's say you apply a force. You don't apply a force. It's actually in the horizontal direction, the force is 0, right? What does it mean? It means that the force of static friction must be 0 as well. Okay? However, if you start increasing this force, this applied force, and the object still does not move, it means that the force of static friction increased as well by the same amount in the opposite direction. Okay? And you keep on increasing this applied force. That's an actual experiment that you can do, okay? It's not difficult to perform this experiment. It's not difficult to perform this experiment. If you increase your applied force to 2 newtons and the object still doesn't move, it means that the force of static friction also increased to 2 newtons. Do you understand what I mean when I said that the force of static friction has a range of values? It doesn't have a specific value, but it can have a range of value. Until, you can keep on doing this experiment until you reach a limit, okay, in which the object is in the verge of motion. When the object is in the verge of motion, it's still not moving. That's when we reach a maximum value for the force of static friction, okay? And this maximum value is given by this equation here, depends on the normal force that the object is subjected to, and depends on a coefficient that can be measured in the laboratory, okay? And if we plot as a graph the variation of the force of static friction against the applied force, you get something like that. A straight line with a slope of 1, okay? As the applied force increases, the static force of friction increases as well, until it reaches a maximum value given by that relation. Once we exceed this maximum value, now the object starts moving. Okay, here's a example, numerical example, right? Because the maximum value of the force of static friction was 3 newtons, if you apply 3.1 newtons, the object is going to move to the right. Oops. And it's going to move with acceleration, okay? With acceleration, velocity is going to be greater than 0. But now that the object is moving, what takes over is no longer the force of static friction, but it's going to be the force of kinetic friction. Okay? So if we plot this graph, it's going to be something like that. The force of static friction increases up to a maximum. Once the applied force exceeds slightly the maximum value of force of static friction, the object starts moving. And now you have the force of kinetic friction, which is usually less than the maximum value of the force of static friction. That's what we know. Can you remember that? In this region, the object is at rest. In this region, the object will be accelerated. Okay, in this region here of the graph, the object will be accelerated. And I'm going to do something else too. Here you go. At this point, remember, at this point right in here, right? At this point right in here, the applied force is exactly equal to the maximum value of the force of static friction. I see. Like that. Any force above this value, the object will be accelerated. Any force below this value, the object will be at rest. That's what this graphic is explaining. Okay. And now let's see. Let's document everything that we said. Okay. Okay. If an object is at rest and if you apply, here you go. If you apply a net, if you apply a horizontal force to an object, and this object stays at rest, remains at rest, let's go step by step, right? Consider an object at rest. Okay, here you go. If you apply horizontal force to this object and it still remains at rest, it still remains at rest, comma. This means that the force of static friction, consider an object at rest over a surface, right? Over a surface. I'm just repeating what I showed to you in graph, in illustration format, right? What I illustrated. If you apply horizontal force to this object and it still remains at rest, this means that the force of static friction, this means that there is a force of static friction that's countering your applied force by the same value. If you increase this applied force, you slightly, you will also observe that the object will still remain at rest, meaning that the force of static friction increased with the applied force. Okay? I'm gonna give some numeric examples, right? If you apply horizontal force of 1 Newton, horizontal force of 1 Newton, okay, of 1 Newton to this object and remains at rest, this means that there is a force of static friction that's countering your applied force by the same value, or minus 1 Newton, right? The negative sign means that the object, the force of static friction is contrary to the applied force. If you increase this applied force slightly, say, to 2 Newtons, and observe, right, that the object still remains at rest, this means that the force of static friction increased by the same amount, or minus 2 Newtons. If you keep on repeating this procedure, eventually you will reach a limit where the object will be on the verge of motion. Will be on the verge of motion. Will be about to move. Okay? At this point, you reached the maximum value of the force of static friction that is given by, let's write it down here. maximum value of the force of static friction, comma, max, right? Let me see here. I'm not going to put a vector there. This is given by mu sub s. I'm going to explain what this mu sub s is all about. Times the normal force applied to the object. Okay, that's the maximum value of the force of static friction. If you increase your applied force past this value, the object starts accelerating, the force of a static friction ceases to exist, and it becomes a force of kinetic friction, F sub k. Okay. This force of kinetic, and by the way, this force of kinetic friction is given by, that's the neat thing about the force of kinetic friction, is the same, has the same format. Okay, it's also given by a coefficient times the normal, but this coefficient is going to be, maybe most of the time is different. Most of the time is less than mu sub s. Okay? Look here, the equation is the same, right? It's just the coefficient that is different. There's those two coefficients, these two coefficients, mu sub s and mu sub k, coefficient of static and kinetic friction, respectively, are called the coefficients of static and kinetic friction, respectively. Okay? Usually, mu sub k is less or equal than mu sub s. So we have the following. Let's here you go. We have that the force of static friction can be anywhere between 0 and its maximum value, right? Or anywhere between 0 and mu sub s times n. And the force of kinetic friction is given by this value here. the coefficient of static and kinetic friction, the coefficients of static and kinetic friction are obtained, are different for different contact surfaces. Okay? What do I mean by different contact surfaces? Okay, so let's say steel on steel, right? Plastic on marble. Okay, what else? Rubber on asphalt. Rubber on concrete, etc. That's what I mean by different contact surfaces. And we can find a table of those coefficients in Wikipedia or even the internet. Here you go, let's take a look. Let's see here. Static and, the book. Let's take a look at your book. Okay, so microscopically speaking, okay, when you have two surfaces under contact, you have some microscopic non-uniformities that produces this friction, okay? If the two surfaces were completely polished, there would be no friction whatsoever. Okay, that's a good way of looking at it. Here you go, he's illustrating exactly what I illustrated for you. As we increase the applied force, the force of the static friction increases until a maximum value. Here, the object is on the verge of motion. Okay, and this force of friction does not depend on the area of contact. Okay, it does not depend on the area of contact. Let's write it down. Okay, the force, by the way, very important, by the way, the force of friction does not depend on the contact area. Depends only on the characteristic of the material. Static frictional force. Okay, let's see. Oh yeah, here you go. That's what I want to show you. Coefficient of static friction, coefficient of kinetic friction. Okay, most of the time it's less than the force of kinetic friction is less than the force of static friction. Most of the time. There'll be times in which they're gonna be the same, okay? Glass on glass, 0.94, 0.4. Ice on ice, 0.1, 0.02. Rubber on dry concrete, 1 and 0.8. Okay, we are talking about the tires of your car in concrete, over a concrete surface. Rubber on wet concrete, right? Look what happens with the coefficient of static friction and kinetic friction. They decrease. Steel on ice, very small. Steel on steel. And so Teflon on Teflon. Can you remember that? Teflon, whenever you have two Teflon surfaces in contact with each other, they have a very small coefficient of static and kinetic friction. Okay, so it's 12:51 now, right? We're going to stop here now. And next time we meet is going to be the exam, okay? If you need any help, I'll be here right now during my office hours. And otherwise, I'll see you the day after tomorrow. See you all. Bye-bye.
Thank you, Professor.
Thank you, Professor. Have a nice day.
Welcome. Let's see. Yes. Okay, thank you. Do you need anything, Jenny?